And all right, for our final talk, we'll have Surbhi from Microsoft Research talking about figures for learning generalized linear models. Go ahead, thanks.
Hey, thank you for the invitation. Can you all hear me?
Yeah.
And see the screen?
Yeah.
See the slides? Okay, perfect. Thank you all for sticking around for the last talk of this workshop. So today I'm going to talk about computational barriers for learning some specific generalized linear models. So let me begin with defining generalized linear models. So I'm going to be calling them GLMs for the rest of the talk, and I'll be talking about specifically some particular kinds of GLMs that I'll make clear. So these are generally just like a class of functions which are parameterized by some unknown weight vector W. So you can think of these as functions that take a high dimensional vector into a univariate value, which is sigma of W in a product X. So this is like a generalization of linear functions where you have this non-linearity sigma added on top of it. And generally it's assumed that the sigma, for our setting, that the sigma is known, and it's going to be some one Lipschitz monotonic function. And most likely it's always usually non-decreasing. So for example, two commonly used functions here are ReLUs, which are sigma of A being max of 0, A. So on the, it's just gonna like truncate on one half of the input. And the other one is a sigmoidal activation, which people have very frequently seen as an approximation to the 0, 1 function, the threshold function. So in this talk, I'm gonna mostly focus on the ReLU. So this ReLU is the full form of that is the rectified linear unit. So I'm going to denote this by ReLU of W, which is the ReLU parameterized by this W function. So as you look in this figure that I have, this ReLU is kind of like interpolating between a threshold and a linear function. So on one half, it kind of behaves like a threshold, and on the other half, it behaves like a linear function. Half spaces we know are challenging to learn, and linear functions are easy to learn. And the reason to focus on this activation function is kind of because this is a building block of neural nets, and this is very heavily used in commonly used architectures. And understanding whether we can actually learn this simplified problem is like a base for understanding for more deeper networks what we can do. So let me just start by defining what I mean by learning here. So I'm going to look at two forms of setups. So one is going to be given access to just direct samples, and you're just doing like an optimization problem on the samples. And the second would be similar to what's been discussed already, which is the statistical query setup, where you'll be given access to queries to the distribution, not directly access to samples. And so your task is to design like an algorithm that takes in this form of input, whether either of these forms of input, and outputs a hypothesis H, which minimizes some notion of loss. And what you want is that the loss of the hypothesis is competitive with the loss of the best weight vector that parameterizes your ReLU up to some additive error of epsilon. And here, this best possible loss is going to be, depending on what setup, is going to be either the test loss or the training loss that we're going to look at. And generally, we're going to focus on square loss, because for ReLU, this makes the most sense to like just look at the L2 distance between the prediction and the actual label. There's another notation that I'm going to use, and which will be important, is going to be the distinction between proper and improper learning. So here, when my algorithm is restricted to output a hypothesis which is exactly of the form of, a ReLU, then I'll be calling it a proper learner, else I'll call it an improper learner. So information theoretically, we think about this problem. The complexity of this model is pretty simple. Like we can just, if we assume that the weights are bounded, we can use any of our favorite complexity measures and be like, okay, this is going to be bounded polynomially in all the parameters of interest that we have in this problem, being the dimension, epsilon, so forth. And you could, like, if you don't care about efficiency, you could brute force over this parameter space and, output the best hypothesis you found. And this is going to generalize. So the question that you actually care about is like, is it possible to do this computationally efficiently? So can we get a computationally efficient algorithm? By computationally efficient, like hopefully polynomial time algorithm that can solve this problem. So before I even talk about computational efficiency of the algorithm, it's important what noise model we consider, that we've seen in previous talks, that the noise model really changes the landscape of the complexity of this problem. So there are three noise models that are generally considered. And the fourth one I don't mention is the Massart noise, which was discussed recently in the talk. So let's go with the first one, which is the realizable noise model. So here you assume, this is a very strong assumption, that you have no noise. So your label is exactly parameterized by some underlying value. The second is this P concept model, which is more commonly you can think of as mean zero noise. So you add like a mean zero noise variable. So you know that the expectation of Y condition on X is always going to be some underlying value. You might never see that value, but that's what it's going to be conditioned. And then the agnostic noise model is this arbitrary noise. You'll assume that Y has no restriction, like it doesn't have to follow any form of a ReLU or something, but then your goal is to fit the best possible ReLU that you could fit on this data. And here you'll assume some basic restrictions on Y being bounded probably, or like some have good tails or something to just make this problem doable. So if you look at the realizable noise model, this is actually solvable in polynomial time by like just doing linear programming to fit this exact function. And under some additional assumptions, you can show that even gradient descent can learn this setup. So you need some assumptions on the distribution, on the anti-concentration and concentration of the distribution. And then you can guarantee that gradient descent can also learn this. Whereas in the P-concept noise model, in fact, this is also solvable in polynomial time. There is a convex surrogate that I actually mentioned in the later part of the talk, that if you optimize on that convex surrogate, you can actually guarantee that you're going to do well in terms of squared loss. And this is from work by Kalai Shastri, Kakade, Kalai Kanadeshmi from the early 2010s. And so in this talk, I'm going to focus on this agnostic setup. So we know that there is, from prior result, that there is no, it's not solvable in polynomial time, but the exact characterization is not clear. And this is what we're going to focus on for this talk. So the question we're going to ask is, what is the precise computational complexity for this problem? And for this, we'll actually look at two different setups to answer this question. So in the first one, I'm going to talk about the first part. I'm going to talk about a conditional hardness result. So this is going to be based on some assumption of a hard problem. And then we're going to say that in the setting where we assume that even the weights are bounded, even the inputs are bounded, like have low norm, can this problem be solved? And we'll show that actually it is hard even in that setup. And we'll get like a precise complexity of this problem. And this is joint work with Adam, Passan, and Daniel. And in the second part, we'll say that, okay, now we don't care about, we want unconditional hardness. Like we don't want to rely on a hardness of a problem, but we're going to restrict our computation model. And this is going to be in the flavor of SQ hardness results. And we're saying, even if we assume that the input distribution is very well behaved, that it's a Gaussian, we'll say that this is actually still hard. And this is joint work with Arvind and Adam. Are there any questions at this point before I go into these two results? I cannot actually hear the question. Sorry.
Elliot asked if part one is for proper.
Yes, part one is for proper. I'll mention that. Yeah. So there is a known, in a previous paper in 2017, we showed for improper, like just generally that there is a lower bound, but it wasn't tight the way we can get for proper learning. And in fact, I'll talk about this more in the result, that there's actually a separation between proper and improper learning. So let's talk about the first part. So let's just redefine the problem for the setup. So we're just going to consider the set of S of samples that we're given. And our goal will again be to minimize the squared loss, but now we're just minimizing the training loss. So it's just like samples drawn from this training set. Now the training problem is equivalent to learning problem if we choose D to be uniform on S. So we're just going to focus on the training problem. We'll show hardness for this training problem, in fact. And note that we're going to, as Elias already mentioned, we're going to focus on proper learning. So we want to output a W that actually fits the best possible label. And to remove the scale of dimension, we'll just assume that the input X is in the unit ball and the Y label is in 0, 1. And even the weight that we're trying to optimize is only restricted to the unit ball. So these are restricted to have norm 1, so there won't be any scale dependence on the dimension. So the main result we're able to show is that under a certain exponential time hypothesis, I'll mention what that hypothesis is. We can show that there's no 2 to the little lower 1 by epsilon square poly in dimension time algorithm for proper ReLU regression up to additive error epsilon. Okay, and the bounds again are poly in D because of the norm bound on the input and the weight. And note that there's a simple algorithm that actually matches this upper bound. What you could do is that you could take your input data and you could just guess what the ReLU sign is going to be on that particular input. And you can iterate over all possible sign patterns and try to fit any ReLU that you can fit, assuming it behaves as well according to the sign pattern. And once you fix the sign pattern, it's like a linear function that you're trying to fit. So you can just do the simple algorithm, and this is given in an approach by Arora et al. In like 2018, and this matches this bound. And note that this actually gives us an interesting separation. So in fact, for improper learning from a paper by me and my co-authors in 2017, we actually know that there is an improper algorithm for this, which runs in 2 to the order 1 by epsilon time, instead of having to pay this 1 by epsilon square. So this actually gives a separation between proper and improper learning for this particular setup, assuming this particular hardness assumption. So what is this hypothesis that we consider? So we look at this problem of densest kappa subgraph. So this is the problem that you're given a graph of size n, and there's a parameter kappa that you're given. And you want to find the kappa vertex graph which has the maximum number of edges. So here on the picture, you can see that the edges highlighted by pink is the subgraph of size that I can find, which has a maximum number of edges. And so we define this notion of gap ETH for this densest kappa subgraph problem. So we assume that there is no, if this is a valid hypothesis, that there is no 2 to the little o of n time sub-exponential time algorithm that can approximate this densest kappa subgraph within a constant factor. So this is the assumption that we make. I'm not an expert in this, but Pasan has done some work on this, and he believes this to be a reasonable assumption. So the kind of motivation for this being a reasonable assumption is that there are these existing lower bounds that show that a little o(n) level of the sums of square hierarchy cannot give a constant factor approximation for this kind of problem for bounded degree graphs. And these kind of reductions come from some random CSPs. So if you could do this, then you could refute some random CSPs that these constructions come from. So this is kind of a reasonable assumption to make. So now if we make this hypothesis assumption, the main challenge is the following, okay? So if we look at an optimal ReLU, and if you wanted to approximate it up to delta parameter, then we could do this argument that I was saying, okay, approximate every weight with delta, you can make a delta net on the parameter space, and you can run in 2 to the order 1 by delta square poly d time by just selecting every particular parameter in this epsilon net and computing your loss and seeing which is the best loss. So when the intended solution is actually almost correct, like think of the realizable setting, when your actual label is from this, then this can actually get you 2 to the order 1 by epsilon algorithm, because note that we care about square loss. So if we have no noise, then you can actually choose delta to be just square root epsilon level of cover that you need, because when you look at square loss, if you don't have any other error, you get epsilon square kind of error. So you could have chosen epsilon as delta as square root epsilon to get epsilon error. So to handle this setup, we cannot look at a construction that actually gives you an optimal solution which has a very small error. So what we need to construct, which is the challenge that we face, was to construct an instance where the intended solution is also far from the label. Just to explain the point that I explained before. So if y was the true label and y prime was the best value you're fitting, so if you wanted to see the difference between the error of the approximation, the delta approximation, and the best value, this would be delta square plus 2 delta, and the distance between the approximation and the true label, the best value. So if this error is like order 1, then this error is going to be delta. And so we will need to choose like an epsilon net, which will be like epsilon fine, not square root epsilon. But if this was really small, if it was like of the order of delta or below, then we didn't have to worry about that, and we could go with the square root epsilon parameter. So this is the main challenge that we have. And this reduction actually, this kind of construction actually gives us this setup. So how do we model this? We just look at, it's a pretty standard reduction. We look at cardinality constraints and edge constraints. And we use the biases really well to make sure that our optimal solution is also going to have constant errors. So if you look at this, this is just if you want this edge to be this vertex to be selected, we want its value to be greater than 0.5 over square root k. And if you want these edges also to be maximized, we would want this to cross this threshold. And note that if you were to optimize this over this norm constraint 1 weight vector, then in fact the loss is minimized when kappa of the coordinates are exactly set to 1 by square root kappa, which actually indicate this this densest k kappa subgraph. And if you put this value of 1 by square root k, you'll notice that this, in fact, the ReLU would just give you a 0.5 by square root k, and here it will give you again 0.25 by square root k, which is very far from 1. So both these constraints are going to have large error. So if these constraints have large error, we can show that it kind of behaves in that regime where you need to be very fine in your cover to be able to actually solve the underlying problem. Okay, so this finishes my part 1. Now the thing is that unfortunately, like here we have to construct this distribution, which is kind of very unnatural. It's like on this Boolean discrete setup. So another question to consider is that if the distribution was more friendly to us, like if the distribution was maybe like a Gaussian and really well behaved, where I couldn't, situate this kind of a problem, can we do something better? And in fact, here we can just go back to the learning problem, and we can assume that our input X is distributed according to the Gaussian. And a reason, apart from the fact that it's a well-behaved distribution, another motivation to study the Gaussian distribution, you may ask, like, why should we look at the Gaussian input distribution, is that there's a lot of work in the neural net learning theory literature that assumes that the input is Gaussian, and then they make other additional assumptions, and they're able to get some positive results because since the input distribution is Gaussian, you can actually get closed form, values of what the gradient is going to look like, and you can get these functions, and it's easier to work with them. So this is a natural assumption to look at. And in this part, we're going to work in the statistical query computation model, and we show that, in fact, here we don't need to make a hardness assumption on a problem, but if we restrict our algorithms, then again, we cannot solve this problem. And in this part, our results will actually extend to sigmoids and sign activations, and which gives us a result for agnostically learning house spaces as well. So I don't think I need to go through I'll just briefly go through the model because Elias already did like a good overview of this model, but just if somebody joined right now. So in the statistical query model, we don't assume that you get access to individual samples X and Y. Instead, you get to make like queries to an oracle. So your learner gets to only access samples to an oracle. So the learner proposes a query, say some query which is on the input distribution, so R to the D times the label, and it returns a value, a real value. And the learner also gets an access to fix a tolerance parameter tau. And what the oracle guarantees to return is that it's going to return a value that's going to be close to the expectation of this the query function up to this parameter tau. And again, you can think of this vaguely as the tolerance as a sample complexity and the number of queries as the runtime complexity of this algorithm. So this is the only way you get access. So you can't really see each individual sample. And the power of this SQ model is it is putting some restriction on the computation model, but it allows for unconditional, without assumption, computation lower bounds, like just assuming a restriction on this computation model. And many standard ML algorithms, again, can be expressed in the SQ language. However, parities cannot be learned in this SQ model. So Gaussian elimination, which really relies on knowing the value of each sample, is not SQ. And there have been some results showing like SGD is also not SQ. But like that's SGD on a very complicated architecture. So like I said, that the previous part allowed for any algorithm, but required a hardness assumption. In contrast, here we restrict the computational model and argue that if we restrict the computation model, we cannot learn this problem. So the main result is the following, that any SQ algorithm for agnostically learning ReLUs needs a super polynomial number of queries or super polynomial tolerance. So here the bounds of from the first case scale with dimension, because now we're looking at the Gaussian input. So the input norms are square root D, whereas the input norms were 1 before. And the exact bounds are the following. So for ReLU and house spaces, we get a lower bound that scales as D to the omega 1 by epsilon to the C. And this constant is some constant in 0 to 1. We didn't optimize this constant. And this improves on previous bounds which were known before, which scaled as D to the omega log 1 by epsilon for both half spaces and ReLUs. And for sigmoids, we get like a D to the omega log square 1 by epsilon bound. No bound was known for this. To just point out that there was concurrent work by Nicholas, Kane, and Zarifis, which also showed similar bounds, and subsequent work that Elias mentioned in his talk, which actually generalizes and tightens this result to more general function classes, and can get exactly the precise constants that we would want here. Note that up to constants, this is tight because you can do polynomial polynomial approximations and get this polynomial method, and you can get this result. Okay, so the interesting part about this result is that our approach is slightly different from general SQ reductions. You can argue that is somewhat, okay, you're somehow constructing the hard case in a more interesting fashion. So general standard SQ lower bounds generally work by constructing a large class of functions that are nearly orthogonal. So here what we do instead is like we, instead of constructing explicitly this class of functions, we use SQ lower bounds for existing families and then construct kind of like an optimization approach that if we could solve this underlying problem, then we could solve the bigger problem. So it's kind of a reduction in that sense that if you had a learner for this GLM, this underlying setup in the agnostic model, then you could actually learn, in fact, a more complex model, which is a two-layer neural network in the realizable model. And we know that this from previous results is actually hard, which gives us a reduction. And here, this two-layer part is really important, that this there's a psi on top. So note that this would be just like a one-layer real value, but we take psi to be a function so that it maps it into a probability distribution. So we can actually get like a Boolean value of which we're learning from. So what we can show is that any SQ algorithm for learning the above neural net in the realizable noise model, this was known before, is that if you were to learn this two-layer neural net, then you needed super polynomial number of queries or super polynomial number of tolerance. And through that, we'll be able to show a reduction. So how do we do this reduction? We use Frank-Wolf. So this is pretty much like doing boosting. So what does Frank-Wolf do? So Frank-Wolf is trying to minimize a convex function in a bounded set. So what this optimization algorithm does is that it has this nice property that it always remains in the constraint set without explicitly requiring a projection. So at any point, it tries to find the point in the set that maximizes its correlation with the negative of the gradient, and then it kind of moves in that direction from your current input to that input. It finds like a point in the middle, and it keeps repeating that. And now the interesting part for our setup is that we are trying to learn this two-layer neural network, and what we can show is that this inner optimization actually just reduces to this agnostic learning problem. So basically what we do is we do this functional Frank-Wolf, which is we run this Frank-Wolf on the function space. And the important part here is that we use the convex surrogate function, loss function, instead of just the squared. You could just do it with the squared loss, but we need this surrogate loss function to handle this non-linearity that we added to the second layer. And this is what the surrogate looks like. I'm not going to go too much into detail, but this is the known surrogate from the 80s for doing these kind of problems. And the update step in the middle just basically turns into solving this agnostic GLM problem on the residual of. So each step you basically fit a new neuron, and you just add it to your function, and then you get some residual of how well you fit till now, and then this is like fitting another point to that, and then you can keep doing this. So to complete this reduction, we have to show like a little carefully that we can simulate the queries using the SQ oracle of the original problem of the queries that we want to make right now. And then we can, by standard convex optimization, we can show that the number of inner loops of this optimization cannot be too many, they're bounded. And if the inner loop was actually efficient to be solved, then we could have solved this two-layer neural network problem, which was a contradiction by our assumption. And the main thing is that the surrogate loss can handle this nonlinearity in the second part, which gives us this reduction. Are there any questions at this part? Okay, so to summarize, we presented two very different looking reductions for essentially the same problem under different constraints. So both have their pros and cons. So the first one gives a separation between proper and improper learning. It holds against all algorithms, but it requires this discrete specialized input distribution. And really it's about proper learning, but in practice, we never do proper learning. In the second setup, it holds unconditionally, even for benign distributions, but it holds only against SQ algorithms, though it'll allow for any kind of improper learning. You're just saying that any as long as the algorithm is SQ, you cannot do this. But what's next? Like, what can we do here? So the main reason, at least the motivation for me to study these lower bounds, is that I would like to avoid these computational barriers under some reasonable assumptions. So these hardness results kind of indicate like what assumptions are not sufficient to get positive results. So, I mean, we could go many directions to see like what kind of assumptions can we make to get reasonable results which are actually meaningful. So, for example, like you can look at a relaxed goal. Like we were very stringent about our hypothesis H, which is going to be like competitive with the best possible hypothesis in our class up to epsilon error. So if we relax this to say like constant, like order opt kind of guarantees, like you can play like a constant factor approximation. Then in fact, you can, there are some results and they've been improved subsequently that you can do these in polynomial time. In fact, just allowing for a constant approximation can actually get you some positive results under like more general distributions, but isotropic log concave sort of distribution. You could also look at like strengthening assumption on the distribution. So there is some result that I have with Adam that shows that if you assume like further that your marginal distribution has some strong eigenvalue decay or like some other additional structure, then you can get more polytime algorithms. So I guess the question is like, what can we do next and what kind of assumptions are reasonable to make here? And with that, I'll end my talk. Thank you so much for listening. And I'm happy to take any questions.
Any questions? Surbhi, one question I had is like, where does the link function, the GLM, like where does that enter into the argument for these results? Like for the second one, it's like it enters into the existing SQ lower bound you use. That's the
yeah. So it's very subtle. Like you could still get a lower bound if you didn't use the this surrogate function and you just use squared loss, but you'll get it against just correlational SQ queries. So the fact is that because we let me just go back a second. So because we add this psi here, we can make the label be Boolean and we can still have hardness against this Boolean label that we are learning. And because the label is Boolean, we can actually tolerate any general SQ queries. So that's the only subtlety, that if you want to handle general SQ, we need like a hardness against this.
Is the reason like if you were allowed to take squares and cubes of y, does that give you some new algorithms or is this a technical barrier?
So if you were doing just squared loss, you could get some benefits if you were to do higher moments. So there is a difference between these two setups. Like with if you were, there's a result by I think Sita and Raghu and Adam that can actually show that you can do something if you were not restricted to just doing SQ queries, and you're allowed like correlation SQ, but you can do general SQ. So there is a difference, but this here you cannot do, like here you're giving a lower bound against all general queries. And for our approach, like we need to handle this nonlinearity. So that's why we need to add the surrogate on top so that the surrogate can tackle this nonlinearity to get a learner for this added extra layer, basically.
As a result of that, you can have the hard class of functions to be Boolean values, and therefore you can prove a generalized lower bound.
Otherwise, you have to do like a regression SQ lower bound, which is more complicated.
Say again, sorry, I didn't catch that.
So like if you don't have the nonlinearity at the end and you do the sampling, this is actually a regression problem, right? So then the SQ theory for regression is a bit different, right?
Yeah. So then I can get you a lower bound with respect to correlational SQ queries only.
Okay.
Yeah, this really benefits us. The label is the Boolean, so like any query can be represented as a general SQ query can be represented as a correlational SQ query.
Any other questions? Let's thank Surbhi again.
Thank you.
And that concludes, I guess,